Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we using this book Neural Networks from Scratch in Python, but we writing everything with a Golang. And in the previous video, I finished with the dropout class, the dropout layer. So we tested it, implemented, and we're going to the next chapter, which is the binary logistics regression. So let's start. Now that we have learned how to create and train a neural network, let's consider an alternative output layer for a neural network. Until now, we have used an output layer that is probability distribution, where all of the values represent a confidence level of a given class being the correct class, and where this confidence sum to 1. So we have the probability distribution across all of the classes that model tries to predict. So in my case, in the case that we're been trying to implement, that was 3 classes. We're now going to cover an alternative output layer option where each neuron separately represents 2 classes. 0 for one of the classes and 1 for the other. The model with this type of output layer is called binary logistic regression. This single neuron could represent 2 classes like cat versus dog, but it could also represent cat versus non-cat or any combination of the 2 classes. And you could have many of these. For example, a model may have 2 binary output neurons. One of these neurons could be distinguishing between person, not person, and the other neuron could be deciding between the indoors and outdoors. Binary logistic regression is a regression type of algorithm which will differ as we'll use a sigmoid activation function for the output layer rather than softmax, and binary cross-entropy rather than categorical cross-entropy for calculating losses. Makes sense. Well, from the names. Sigmoid activation function. Okay. I've been waiting for the sigmoid because one way or another you need to face the sigmoid here. The sigmoid activation function is used with the regression because it squishes a range of the outputs from negative infinity to positive infinity to be between 0 and 1. I hope there will be, yes, there is 1. The bound represents the 2 possible cases. The sigmoid equation is 1 divided by 1 plus e in minus x. For the purpose of the neural network, we'll use our common notation. Yeah, so it's 1. So the sigmoid value equals to 1 divided by 1 plus e in the power of z value. The denominator of the sigmoid function contains e raised to the power of z, where z given indexes means a singular output value of the layer that this activation function takes as input. The index I means the current sample, the index j means the current output of the samples. For example, if we'll have, when we'll try to use the actual prediction, we'll have only one row. When we'll try to use the model to predict the values, we'll have one row and several columns representing each output. But while we have the model training, we have many samples with number of the outputs. Yeah. And you can see that, okay, let's go. If we plot the sigmoid function, it goes like this. The interesting part that it never will be equal to 0 and it will never be equal to 1. So it kind of lies in between of this range. Also, there is an interesting one that everything, like, how to say, those values like for these x values, the result function is more or less the same, but the main actually difference in the output value is somewhere around 0 value. And it kind of, the sigmoid function, at least my understanding, it could help you to kind of combine big values in, in one part of the, then combine the other big values in another part. So for example, the negative and the positive, but something in between, you can, it will lie down here. Now the output from this function average at 0.5 and squishes down to a flat line as it approaches 0 and 1. The sigmoid function approaches both maximum and minimum values exponentially fast. For example, for an input of 2, the output is approximately 0.88, which is already pretty close to the 1. With the input of 3, the output is 0.95 and so on. It's also similar for the negative values. So this property makes the sigmoid activation function a good candidate to apply to the final layers output with a binary logistics regression model. So it will shift your values closer to the 1 or to the 0. And only around this place it will be hard to distinguish. For commonly used functions such as the sigmoid function, the derivatives are almost always public knowledge unless you are inventing a function you won't need to calculate derivatives by hand, but it can still be a good exercise. The sigmoid function's derivative solves to Q. If you would like to leverage this fact without diving into the mathematical derivation, feel free to skip the next section. No, I would like to dive it. Okay, the sigmoid function derivative. Let's define the derivative of the sigmoid function with respect to its input. So we have this is the input, z, well, z value is the input. So we have d sigmoid over d zi. At this point, we might start calculating the derivative of the division operation, but since the numerator contains just the value 1, the whole fraction is effectively just a reciprocal of its denominator and can be represented as its negative power. So this is like x in minus 1. Why do we need this? Because we can think of this as the function in power of minus 1. I think this is, yeah. It's easier to calculate the derivative of the power operation than the derivative of the division operation. So let's update our equation to follow this. So this part is the same. So minus 1, it means that we have 1 divided by the value inside the power. And that is because of the negative sign of the power. Now, we can calculate the derivative of the expression raised to the power of minus 1, which equals this exponent multiplied by the expression itself raised to the power lowered by 1. Then, following the chain rule, we have to calculate the derivative for the expression itself. So this is what we're going to have. So we have the minus 1 as this one. We have the function in the lowered with the power lowered by 1, so that will be minus 2. And then we need to calculate the derivative of the function itself. So this is the one. So already around the derivative of the sum operation is the sum of the derivatives. So that will turn into 0, and then we need to calculate this one. The derivative of 1 with respect to z equals 0, as the derivative of constant is always 0. The derivative of the constant e raised to the power of minus z equals this value multiplied by the derivative of the exponent. So we have this as we calculated before, that turned into 0. Then we have the value itself, right? And then we need to calculate the derivative of the internal function. The derivative of minus z with respect to z equals to -1, as the -1 is the constant that we can move outside of the derivative, leaving us with the derivative of z with respect to z, which as we know equals to 1. This is what we get. So we have the minus, then we have um, the value from the first derivative, then we have the exponent itself as the second one, and then we have minus from the last one. Now we can move the minus sign outside of the parentheses and cancel out the other minus. So this is what we have. This one. But I think we can open the parentheses. No. Let's write the resulting equation. The expression raised to the power of -2 can be written as the reciprocal raised to the power of 2. Then the multiplier, the value we multiply by from the equation, can become the numerator of the resulting fraction. So that comes here, that goes into the denominator. The denominator of this fraction can be written as the multiplication of the expression by itself instead of raising it to the power of 2. Why? To split it. Okay. Now we can split this fraction into two separate ones, one containing 1 in the numerator and another one e to the power of -z, both having each of the expressions that are separated by the multiplication operator and denominator in their respective denominators. We can do this as we perform the multiplication operation between both fractions. So we have this one and we have this one. That looks familiar, right? So this is basically the sigmoid function itself. The original one, this one, right? Right. And then again, we have the sigmoid function multiplied by the e in power of -z. If you remember the equation of the sigmoid function, you already see where we're going with this. The multiplicand, the value that is being multiplied by the multiplier, is the equation of the sigmoid function. Let's work on this equation further. It could be ideal if the numerator of the multiplicator could be represented as some sort of the equation containing the sigmoid function's equation as well. Okay. What we can do is to add 1 and remove 1. Okay, so this one. What this allows us is to split the number. Oh, okay, nice. So this is the sigmoid function, this is the 1, and this is again the value of the sigmoid function. Then we know the value we are subtracting of the multiplicator equals 1 as the numerator and the denominator of the fraction are equal, and the subtrahend, the value we are subtracting from, is actually the equation of the sigmoid function as well. So yeah, we have the sigmoid value. It turns out the derivative of the sigmoid function equals this function multiplied by the difference of 1 and this function as well. This allows us to easily write the derivative of the code, but yeah. And so when we'll need to calculate the derivative on the backward pass, will have the values from the forward pass, which is the calculation of the sigmoid already. So to calculate the backwards results, we just need to take these values and multiply them by 1 minus this value, the same value, and that's it. Should be pretty easy. As with other activation functions, we will write the forward path method and the backward path method. For the forward path, we will take the inputs and apply the sigmoid. For the backward path, we'll leverage the sigmoid function's derivative, which, as we figured out during the derivation of the sigmoid function derivative, equals the sigmoid output from the forward pass multiplied by the difference of 1. So I assume that, yeah, derivative calculates from output oh yeah, having the multiplication. So this is the derivative, the previous derivative from right to left, and this is actually the derivative for the sigmoid. Now that we have the new activation function, we need to code our new calculation for the binary cross entropy loss. Okay, so we need to implement. What is this? Is the activation? Do I have the activation? Rel softmax sigmoid. Go. Is it correct name? Sigmoid. Okay. No. Okay. Softmax activation. Okay, that will be type sigmoid activation. This interact, and we'll have the. Do we need the inputs? Yes, we have. We need the inputs. As math we need a public output. And the way is it output, right? And we have the inputs, which is same. Then again, we need to have the forward pass func that will operate on the activation of the sigmoid forwards, and it will take inputs as dense. And okay, activation, and then we have again activation sigmoids backward d values, well, d values again dense. There is nothing else. Okay, so first we store in the inputs for the next calculations. Then we need to calculate the output. The output will be the same size of the inputs. So we need to allocate this, and it will be dense copy of inputs just to make it the same size. But then I'm using the output lie. It will be fun. This one and activation. But we not using the, well, actually we can. Yes, we can. So the result will be from 1 divided by 1 plus, what's it, mass exponent for b minus b. Wait. Right. Takes the power. Yes. That's it. That's it. Then we need to create the, or calculate the d inputs. D inputs will be the same as D values. And then we need to the inputs again apply func D value. We're taking the D value. So what we're doing, this is, we're taking the D value, then we multiply it by 1 minus, I need to take the inputs at the same position. So it should be activation inputs at right? And then multiply it by an activation inputs at. Oh no, the outputs, not the inputs. Why do I need inputs? Uh, out, output, and output. Save the input. To be honest, I'm not sure why I'm storing the inputs here, but okay. Let's just make it consistent. Yes. Now we go into the binary cross-entropy loss. A binary cross-entropy loss. To calculate binary cross-entropy loss, we will continue to use the negative log concept from the category cross-entropy loss. Rather than only calculating this in the target classes, we'll sum the log likelihoods of the correct and incorrect classes for each neuron separately. Because class values are either 0 or 1, we can simplify the incorrect class to be 1 minus correct class, as this inverts the value. We can then calculate the negative log likelihood of the correct and incorrect classes, adding them together. We can then calculate negative log likelihood of the correct and incorrect classes, adding them together. By presenting two forms of the equation, the first is following the description just given, then the optimized version differentiating only in the minus sign being moved over and redundant parentheses removed. So this is what we have. We have the output multiplied by logarithm of this value minus 1 minus the value multiplied by the logarithm. Oh, no. No. Y is the correct class. This is the logarithm from the predicted. And then again, 1 minus the predicted class multiplied by logarithm from minus 1 minus predicted. Since a model can contain multiple binary outputs and each of them, unlike the cross-entropy loss, outputs its own prediction, loss calculated on a single output is going to be a vector of losses containing one value for each. What we need is a sample loss, and to achieve that we need to calculate a mean of these losses for single sample. Since a model can contain multiple binary outputs, unlike in the cross-entropy loss outputs its own prediction. So, I mean, in the category cross-entropy loss, for when the model tries to predict, it creates the vector of the probabilities for each class. Loss calculated on a single output is going to be a vector of losses containing one value for each input. Single out is going to be a vector of losses containing one value for each input. One value. So instead of vector, going to be a vector of losses containing one value for each. What we need is a sample. I don't get it. How it's different. Wait. Where index I means the current sample, index j means the current output in the sample, and the j and the big J means the number of outputs. Since we're operating on the set of sample, the output is in the ring containing the set of the loss values, we can use the numpy to perform this operation on a single call. This is the mean. This is the mean value across all of the samples. Well, across all of the outputs for each sample, right? The last parameter x is equals to -1 informs numpy to calculate the mean value along the last dimension. So the second one. To make it easy to visualize, let's use a simple example. Assume that this is an output of the model containing 3 neurons in the output layer and is passed through the binary percent. We have this one. Those numbers are completely made up. For example, we can take each of the output vectors 1 to 3, for example, and calculate the mean value from the numbers they hold, put in the results. Okay, so it actually goes row by row. Using numpy, prints. Okay, this is mean values. Sum is 30 and 10. Okay, so we're actually going through calculating mean value for each row. If we calculate the mean value of the first output, it's indeed 2. The mean value of the second output is 4, and so on. We're also going to inherit from the loss class, so the overall loss calculation will be handled by the calculate method that we already created for category cross entropy loss class. Well, I don't have the inheritance, so I probably just copy paste it. And that's it. For now. Then I will make it better. But let's see how it will go today. To calculate the gradient from here, we already know the derivative of the natural logarithm is 1 divided by the value, and the derivative of 1 minus x is minus 1. To simplify the form, this gives us true probability divided by the predicted probability plus 1 minus true probability divided by 1 minus probability, and all it multiplied by the minus 1. Calculate the partial derivative of this loss function with respect to the predicted input. We will use the later version of the loss equation. It doesn't really matter in this case which one we use. Okay, the expression that was presented before. So this is the formula, and this is the way that we're writing. So we're calculating the derivative with respect to the predicted values, and we treat the correct predictions as constants. The expression that we have to calculate the partial derivative of consists of two sub-expressions, which are components of the sum operation. We can write these as the sum of derivatives. This one, yeah, this is just a sum. Well, any not subdivision, any subtraction is another addition with minus sign for the second one, or for the first one. So we're just writing the sum and putting the minus sign from here into here. So this is actually minus 1 multiplied by this one. Both components contain predicted values, the target values inside of the derivatives, which are the constants that we're deriving with respect to y hat, which is the predicted values, which is a different variable. So we can move them outside of the derivative along with other constant and minus sign. So this is how we moved it. So this is the const. We moved it from here outside, and then we calculated the derivative from the logarithm. Then we here doing the same. Again, this plus sign makes the minus. This, as we treat it as a constant value, so we moving it outside because of the multiplication, and then calculating the derivative from the logarithm. Now, like in the category cross entropy loss derivative, we have to calculate the derivative of the logarithmic function, which equals the reciprocal of its parameter multiplied following the chain rule by the derivative of its parameter. Let's apply that to both of the partial derivatives. So we have 1 divided by y hat is the derivative of the logarithm. 1 divided by 1 minus y hat is again the derivative of the logarithm itself. Then we need to calculate the derivative of the underlying function itself. So here in this case, now with the first partial derivative, that equals to 1. The second partial derivative can be written as the difference of derivatives. So we have this turned into 1, then we have this over here multiplied by this from here, and then we're writing it as the difference. So that will return into 0, that will turn into 1 and -1. So yeah, this is what we get. We can finally clean up to get the resulting equation. What we have? We have the target prediction divided by the prediction plus, again, let's just take it like this. So we have minus. I mean, why not just to put the, I mean, you can change them. You can write this minus this. Oh, no. No. Yes. So if you put the sign into the parentheses, that will be minus this one plus this one. So you can exchange them, then this minus this. The partial derivative of the binary crystal loss solves a pretty simple equation that will be easy to implement with the code. Partial derivative is a derivative of a single output's loss, and with any type of output, we always need to calculate it with respect to a sample loss, not an atomic output loss, since we have to calculate the mean value of all output losses in the sample to form a sample loss during the forward pass. So then what is the big J? For backpropagation, we have to calculate the partial derivative of a sample loss with respect to each input. We have just calculated the second derivative with the partial derivative of the single output loss with respect to the related prediction. We have to calculate the partial derivative of a sample loss with respect to single output loss. 1 divided by j, the number of the outputs, is a constant, can be moved outside of the derivative. Since we calculated the derivative with respect to given output, the sum of one element equals to this element. So this is what we have. The remaining derivative equals 1 as the derivative of a variable with respect to the same equals to 1. So the full solution is, now we can update the equation of the partial derivative of a sample loss with respect to a single output loss by applying the chain rule. Okay, so that was to the outputs, and right now that's the derivative to the single output. You have to perform this normalization since each output returns its own derivative, and without normalization, each additional input will raise gradients and require changing other hyperparameters, including the learn rate. So then code. We have the number of samples, number of the outputs in every sample. I don't need this. I can take this from the dimensions. Then we calculate in the gradient. So the inputs is y true. Not correct. The true probability is divided by clipped d values and then minus the opposites and divided by outputs. And all of this divided by the outputs to normalize. Similar to what we did in the categorical entropy loss, we need to normalize gradients so it's become invariant to the number of the samples we calculated for. Normalize gradients. Finally, we need to address the numerical instability of the logarithmic function. The sigmoid activation can return a value in the range of 0 to 1 inclusive, but can you get the 0? Random slight issue due to how it's calculated and will return negative infinity. This alone isn't necessarily a big deal, but any list with minus infinity, it will have a mean of minus infinity, which is the same for any list with a positive infinity origin infinity to mean. But Oh, okay, so that was okay. We had the same for the categorical set replace when in some cases the prediction is fully zero. This is the similar issue we discussed earlier regarding categorical center loss in the chapter 5. To prevent the issue, we'll add in clipping on the batch of the values. Clip data to prevent division by zero, clip both sides to not drag mean towards any value. Okay. We now will use the skipped values for the forward pass rather than the original. That's the same as we had in the categorical center field. As we perform the division operation during the derivative calculation, the gradient passed in may contain both values 0 and 1. Either of these values will cause the problem in either this one, respectively. So we need to clip this gradient as well. Okay. So we have the predictions and we have, okay. Now, similar to the forward pass, we can use the clipped values. Simple losses. Okay. The full code now for the binary cross entropy. Binary categorical. Okay, I'm checking the time. I probably will start where I have it. Loss. This is the activation. Categorical cross entropy loss. Okay. And the next one is binary. I will start implementation and continue in the next one, probably. So what we have, we will have probably something the same. Boom, boom. That's not the categorical cross entropy, that's binary cross entropy loss, right? And then we have the calculate function. I will copy it for now, but ideally I should make something to reuse this function. Okay, and then we will have forwards that will predict it and true values. It's basically this one. The only difference is we will have the binary. And again, and then we have the backwards. Should be same. Okay. Turn. Make. Now we have the D inputs. Okay, we have the D inputs. Okay, so let's start from this is the backwards. Okay, we have the prediction clip basically the same, right? Math. We have the predictions clipped. Then we calculate in the sample. Why true, why predicted? So they all... No, this is two-dimensional, this is two-dimensional, but that's one-dimensional, right? Because then we go in through sample losses and calculating the sum. Okay, so I will have... It's not the sample losses. I think that should be... Wait. Calculate sample-wise loss. Okay, so the predictions is actually... I'm trying to remember. Okay, where it's used. No, okay. Okay, how do we calculate? Okay, let me take a look at recording time because I might... Maybe I will finish early. That's incorrect. It's already declared. No. Ah, yes. Sorry. Binary. Okay, since the recording time getting close, I won't finish it anyway, so I will do this in the next chapter, in the next video. But what I need to remember? I need to remember what's the input, and I mean, we go and we take in the output right here, calculating accuracy, but the loss activation function returns the probabilities of the... I mean, I'm still trying to remember if it's a two-dimensional, one-dimensional array. Accuracy. We have the loss activation, we have the forward, and we use the categorical centripetal loss and calculate the softmax, set the row. Okay, so that's two-dimensional one. Okay, why I'm trying to remember all of this? I'm confused by this one because, I mean, that's kind of two-dimensional because we have with the concrete value. I guess I need to convert it into the one hot array because here the predicted, at least now. Okay, maybe we're going to actually change it. I mean, what confuses me is that at least in the categorical centripetal loss, the y predicted that goes from here. For example, okay, where it's used to calculate, it's used in the forward method. What it takes the output of the activation function, which is the two-dimensional, and it takes the y, right? And here, what it does, it calculates the forward, what is the forward is? It makes the copy, well, adjust the values, but it's two-dimensional. Then we calculate the confidences. Prediction clicked. Okay, so we're actually using it one, and then we pick in, yeah, I remember this. We pick in the, so we're going through the targets. But yeah, so the prediction is a two-dimensional, and then we convert it into the confidences as the one-dimensional that contains only probabilities against the correct class. And then we calculate the negative likelihoods, which is kind of the same. It's a little bit different. Okay, probably I will check how it's used here. And that's it. Also calculate activation, the prediction. Okay. Okay, this not clear for me, these parts. Maybe I will debug it. My main question is, well, the y true, how they get the y predicted. And probably that will answer all of my questions because I know how to calculate, I know how to write this one. That looks like it should be, at this moment, the sample losses should be a two-dimensional. But then the question, what do we do with the y true, which is the one-dimensional? So, okay, but yeah, maybe I'll just reread this and do it once again. But that's okay. Sometimes that happens, that it feels like there is no progress, but there is actually a progress. The main thing is to do it every day. So probably tomorrow I will fix with this one and go for the next chapter. Yes, into the next chapter. Thank you for watching, and I see you tomorrow. Bye-bye.